Eli Shellabarger is an aerospace engineer at the Atmospheric Flight and Entry Systems branch at NASA Langley Research Center. Eli received his bachelor's and master's of science in aerospace engineering from Iowa State University in 2017 and 18, respectively, with focuses on experimental and computational fluid dynamics. Prior to joining NASA Langley in April 2021, Eli worked at Textron Aviation and the spaceship company / Virgin Galactic with a focus on aerosciences and advanced design.
Thank you for the introduction. As has been mentioned, my name is Eli Shellabarger, and so today I'll be presenting some work that I've been doing on working towards a predictive capability for entry capsule dynamic stability characteristics within Fun3D using reduced free flight motion. You can go to the next slide. So a little bit about the motivation for this work. Currently, there are multiple entry, descent, and landing flight projects that are working to characterize their dynamic stability. Among those is the Dragonfly mission to Titan and the Mars sample return mission, specifically the Earth entry system that we were just hearing about. And although these are very large and important missions, there's still just limited access to in-man ground test facilities, as we're not the only ones that want to use them. And so anything we can really do to expand our predictive capabilities is extremely useful. And so with that in mind, there's been a lot of focus on using free flight CFD just as a method to both get better insight into what those ground tests are giving us, running cases that we're not able to replicate in a ground test facility but are relevant to flight conditions, and finally isolating anything that maybe we can't see in a ground test but we can get out of CFD. Free flight CFD also gives us the ability just to constrain the problem a bit and make it a bit more focused on the things that we're interested in seeing and isolate the degrees of freedom that can be considered minor enough to eliminate. And so the current work that I'm showing here is really working to verify that the current approach is working as expected and begin applying it. Concurrent ground testing efforts will provide a treasure trove of validation data that we can then feel confident about the current analyses and also prepare a workflow for future applications. Next slide. So here's just an outline. I'll skip over this since we're a little behind, but next slide. So a little bit about the background behind this dynamic stability characterization in general. When approaching a new flight project, generally the first thing we're gonna do is look at what has historically been done. However, there are some drawbacks to this approach. Among them is just the degradation of the data that we have access to. And this just comes with time. One good example that I have here at the top of the screen is even with our historical test reports, as things have been migrated to digital servers, there's a natural loss in fidelity of that data just as they're scanned onto the archives. I've got a comparison here from the Genesis ballistic range test report, where the images on the test report are shown on the left, and then a rescanned film from the shadow graph of the test is shown on the right. And as you can see, there's just a lot more information about what's going on in the flight test, or the ground test, for this case, in the rescanned image, but sadly those rescanned images aren't always available. When we do need new data, then we can go to ground testing facilities, and these are things like the wind tunnels we have access to here at NASA Langley, such as the vertical spin tunnel or the transonic dynamics tunnel pictured at the bottom of the screen. However, these are, again, as I mentioned, very large facilities. They're often hard to get access to, and they just have the inherent limitations of ground testing that we can only get to the conditions the tunnels are designed for. This is also true of ballistic range tests, where we can only hit the conditions that are able to be targeted within the span of a flight across a range while staying within range safety protocols. So this has driven a lot of people to focus on creating a computational approach, and I'll mention some of the other really great work that's been done so far in this vein. Among them is the Entry Systems Modeling Group at Ames Research Center, working with Free Flight CFD and US3D, and I'm actually doing quite a lot of correspondence with them, since the goal of this work is not really to compete with them, but just to enable another approach to validation so we can have multi-code fidelity and verify things with multiple paths and really feel good about the answers we're getting. There's also work to couple post-2 to Fun3D, and this is more of a macroscopic approach to things and not really in the dirt 6DOF right on the right in the CFD solution. And finally, there is the overflow 6DOF path. The drawback to overflow, however, is that it's a structured solver and requires a fair amount of model prep time to actually get something going. And so that is why we're using Fun3D. Next slide. So a little bit about the solver we're using here. Fun3D, for those that don't know, goes back to the late 1980s, and it is an unstructured solver. That's incredibly important for the current applications as it greatly reduces the model preparation time. It's also developed here at NASA Langley, which just reduces any roadblocks and getting things going, as we're able to directly collaborate with the developers on getting this capability up and running. It's also just already widely used across government, academia, and industry, which helps improve our confidence in the results that we're going to get out of the code, and already being actively used in capsule aerodynamics and EDL technologies for those reasons. So it's got a track record that we can kind of go back on. It also just offers a multitude of different approaches, and I've got some examples of those on this slide. The video on the top, which should hopefully play automatically if you have once more, or just play it. But the video on the top is a comparison using DDES to some active ballistic range testing that we have on the Earth entry system, showing some pretty good qualitative agreement between the solution and the ballistic range conditions at Mach 2. And on the bottom is just an example of another additional approach that we get access to through Fun3D. That one's just an image, but using an adaptive RANS path to get some automated grid sequencing and just get more confidence in the answers that we're getting. Now, the 6DOF library that is in Fun3D, it was developed by Kumalo et al. And this was coupled to Fun3D in the late 2000s. However, there's been very little documented use to this library. I think I can count the number of people that have used it on one hand. And so for that reason, it required a bit of rediscovery for the current applications. Next slide. So for that verification, to just start to build confidence, I started with something fairly simple, which is just an inviscid falling sphere case. Since this has an analytical solution, and you just start by verifying that things work as expected. And in the plot down below, you can see that things are indeed working as we expect. Then the video on the right just shows that same falling sphere case, but applied to a viscous model at Mach 0.5, just to really create a qualitative check to make sure that the simulation is expecting as behaved. We get the expected motion where we're falling downwards with a bit of blowback from the fluid motion in the simulation, and just seeing that the wake and everything moves as expected. Next slide. From there, we were then able to, or I was able to move on to running the Army-Navy. The inner geometry in this test case was provided by the Georgia Tech Post-2 Fun3D team. And so this case uses the built-in Fun3D 6DOF, both on our side and the Georgia Tech side. Georgia Tech originally ran this case a few years back as a verification for their framework as they were getting ready to implement Post-2. And so for us, it works as a verification case that the Langley native builds of the solver, or the coupled solver, work as expected. And on the plots on the right, you can see that we're getting great alignment with their solution, just verifying that, again, everything works as expected. Next slide. And so finally, the last verification case before moving to applications is moving to three-dimensional blunt bodies. In this case, it's being run on the Genesis ballistic range model from those same cases that I mentioned previously at Mach 1.44 and sea level. And so this case is just a free-to-pitch simulation, and the goal here is to extract the predicted pitch accelerations and make sure that both the forces and velocities on the body are just in good agreement as the last sanity check to make sure things come out correctly. If, let's say, improper scalings are being applied, these values wouldn't match, and so that's something that we wanted to make sure everything was working as expected. And so you can go to the next slide. And just a video of this case that's being shown here. So that brings us to actual applications of the solver. You can go ahead and play the video. So in this first application, this is on the Dragonfly entry capsule. Now this case that's being played on The right is at Genesis ballistic range conditions and using the ballistic range model mass properties. This is because Dragonfly shares a fairly similar shape to the Genesis entry capsule, and therefore we can lean on the ballistic range model we have from Genesis as some prior data, similar to how I mentioned the first thing we ever do with the model is just looking at what has historically been done. And so this model starts at 30 degrees, again at that Mach 1.44 case, and allows the model to just pitch down as time runs on using a RAN solution. This work will also be continued on to a variety of TDT conditions as Dragonfly is undergoing active TDT testing. Next slide. Another application of this work is on the Mars Sample Return Earth Entry System, and this is largely in conjunction with the active ballistic range testing that we are doing on the Earth Entry System. And so the case that I'm showing here is at a similar Mach number, but different pitch angle to the image on the left. And this is just the model starting at initial angle of 20 degrees, Mach 2 at sea level, same as our ballistic range facility, and allowing the model to pitch damp down, in this case, run out for a shorter duration than the previous Dragonfly model. And this work will also be expanded in the near future to TDT testing as EES recently wrapped up some testing in the TDT facility. Next slide. And so that brings us to just the future work that we have ahead of us. So the first thing to do here is establishing a data reduction pipeline. None of these simulations mean anything if we can't extract the dynamic stability coefficients from them, and so that'll be some upcoming work, and again, where I'll be collaborating with the US 3D folks who have already been working in this field to make sure that we're using similar methods, and really just establishing a variety of ways to reduce that data so we can also evaluate the uncertainty behind it. As I've hinted at a couple times here, there'll be some upcoming work to expand to lower transonic Mach numbers and free to pitch simulations, and this is to leverage that TDT data that's becoming available to us. And then that also brings us to expanding the current work to scale resolving simulations such as DDES. This is really to refine the backshell contribution to the dynamic stability. However, there is an issue with the large temporal difference in scales that we have to deal with in those situations. An example of this is the video on the right, which is the EES at the same Mach 2 condition as the prior slide. We're running with a DDES model, and as you can see, there's a large difference in the scales that are occurring in the aft wake compared to the body motion itself. And so this is really a huge hit on the computational intensity of the simulations. Finally, as I mentioned at the start of this presentation, a lot of work will then be coming up on or to use this data for just validation by the ground test data that's being gathered at the same time, along with comparing this work to solutions from other solvers. That'll help us really get a concrete understanding of how this solver can be used, where its strengths are, where its weaknesses are, so that it can be continued to be applied for future flight projects. Next slide. So that kind of brings us to the end of things here with the fact that the 6DOF solver, which really has not seen much use, is starting to be brought back into active work at NASA Langley, largely with the focus of use on dynamic stability characterization. There've been a fair amount of verification efforts at this point that have really made us feel comfortable using it on flight projects, and the ground test data that is coming from those flight projects will then enable us to validate the solver and have continued comfort in its use for current and future applications. And so I'll just give some acknowledgement here to the NESC for funding work for both getting this segment of the code back up and running and also its applications to the Dragonfly project. And next slide is just references. And then